Section 22.3, Magnetic Flux. If we continue from our last section on motional EMF, we'll find if we take a closer look, it actually closely relates to this idea of magnetic flux. So we'll start with the equation that we got for the motional EMF that's equal to the speed that the rod is moving at times the magnetic field strength times the length of the rod. But we're going to work in slightly different terms here to help us define the magnetic flux. So we're going to focus on that its speed, as it's moving to the right, you could describe as a change in position in x, right? It starts out at some initial position, x naught, and it's later at some final position, x. It's covered that distance. And that's over a time interval, right? From some initial time, t0, to some final time, t. So we can write our velocity as the change in position over the change in time, x minus x0 divided by t minus t0. Cool. The next thing we can do is we can take this length and factor it, distribute it, to be multiplied next to each of those x's. So then we'd have x times L minus x0 times L. And the thing that we might start to notice is if you have the initial x times the length, right, that's just going to be whatever area this is. Right? If we multiply length times the width as XO, then that gives us an initial area AO. Similarly, if we have the final X times again that length, now we're going to have this whole area in red, which we could just call A. A. So instead of writing X times L, we'll just write A. So we have A minus the initial area divided by T minus the initial time times the magnetic field. And now we'll multiply this magnetic field, distribute that out to each of the terms so that we have the magnetic field times the area minus the magnetic field times the initial area, all divided by the time. And this magnetic field times area is something we are going to focus in on. This covers a concept known as magnetic flux. So we briefly saw electric flux previously, now we're bringing in magnetic flux. So it's our same TIE fighter symbol, which is a capital Phi. And it's equal to the magnetic field times the area, as long as they're perpendicular to each other. With this idea of magnetic flux, we could write our EMF as the final magnetic flux minus the initial magnetic flux divided by the time, or as the change in magnetic flux divided by the time. This is something that's going to reappear in Faraday's law in a more rigorous form. For now, though, we want to focus in a little bit more on this idea of magnetic flux. And I mentioned offhand that it's equal to the magnetic field times the area when the two of them are perpendicular to each other. But what about when they aren't perfectly perpendicular? Well, then we'll need a slightly more advanced definition. And that's that instead of dealing with just magnetic field times area, we're going to also have to multiply by cosine of the angle. Your angle here is phi, lowercase phi, and that is the angle between the magnetic field vector, B, and the normal to the area. So if you have a flat surface area, the normal to it is what's poking out of it. And we want to know how much of an angle the magnetic field makes relative to this normal. So we get a larger magnetic flux when most of the magnetic field is at a small angle, the smallest being 0. That's when we have cosine of 0, which comes to 1. That will maximize our magnetic flux, because the way to think about the magnetic flux is it's the amount that's passing through, right? How much magnetic field is piercing whatever area of interest we have. So the cosine of the angle gives us how much of the magnetic field is going straight through, as opposed to the magnetic field that would just be skimming along the surface here, which would be the other component of it, and that's definitely not piercing it. So the only part that we care about is the component of the magnetic field that is in alignment with the normal to the surface. Let's look at this for a few different cases to see if we can figure out this angle so that we can get some practice here. So what is the angle phi for the following three cases? I want you to look at this, see if you can come up with an answer for all three of them before you move on. So go ahead and pause the video now. All right, hoping you already came up with an answer. If we look at this first one, we notice that the coil, the loop here, right here is shown as a 3D circle, right, has the lines passing straight through it. And the normal to the coil, shown with this dotted line, is exactly in alignment with the magnetic field lines. So this is an angle of 0 degrees. In the second example, the magnetic field lines are going straight down, and the normal is now offset by 60 degrees. So this is one that's also just 60. Notice, because it's a larger angle, less of the magnetic field lines are going through. Finally, in this last one, the magnetic field lines aren't able to pierce it at all, and the normal is at a right angle to it, or at an angle of 90 degrees. We can see this with an image that's very similar to this from the textbook that just shows the coil as a solid side view. So let's take a look at that. The advantage of this view is it shows that when you have an angle of 0 degrees, then you maximize this blue shaded area, the magnetic flux that you get. When you're at 60 degrees, now we have less magnetic flux, shown by the smaller blue area. And when you're at an angle of 90 degrees, 0 flux is given there, right? It's no shaded region. So that introduces how you can figure out the angle by determining the direction of the magnetic field lines and what angle they're making relative to the normal, the perpendicular intersection of your area of interest. One more note on magnetic flux. Graphically, we can interpret what's going on with magnetic flux by the number of field lines that pass through a surface, right? That's what I mentioned before, that we care about how much the magnetic field lines are piercing a surface. Well, we can show that there's more magnetic flux by drawing more magnetic field lines piercing a surface. Similarly, we can show less magnetic flux by having less lines piercing that same surface. So this can help when you're trying to understand figures and pictures and represent magnetic flux in a graphical way. This magnetic flux we will see is the crux of the next section, where we'll take a look. Stick around.